Compound Characterization, Proton Nuclear Magnetic Resonance Spectroscopy, Spectra Interpretation, Part 2. In the previous webcast, we discussed how you can pull a great deal of information out of a proton NMR spectrum. Examples include chemical shift, integration, and multiplicity. In this webcast, we will discuss the final piece of information you can pull out of a proton NMR spectrum: coupling constants, also known as J-couplings. A coupling constant, or a J constant or a J value, is the distance between peaks in an NMR signal. This distance must be measured in Hertz. It is a quantitative measurement of the magnetic influence of neighboring hydrogen. For example, if a neighboring hydrogen has a large amount of magnetic influence, then you should expect a correspondingly large coupling constant. This J value is independent of the strength of the spectrometer. This is why it is measured in Hertz. In the same way that splitting is reciprocal, the J value for the splitting must also be reciprocal. If HA splitting HB has some coupling constant, HB splitting HA must have the same coupling constant. Let us look at these proton NMR signals at the bottom of this slide. Here we see that in these particular signals, we have these numbers, these values above each of these peaks in the signals. These values correspond to the exact ppm value of each peak. To calculate the J value, based on this definition up here, the distance between the peaks, you might think that this will be as simple as taking value 1 and subtracting value 2. However, there is a caveat here. What you need to remember is that this value must be measured in Hertz, where these values are all in parts per million. How do we convert parts per million into Hertz? We'll discuss this on the next slide. Before continuing, one note. For this course, when we talk about coupling constants, we are talking specifically about what are called simple first-order coupling constants. Simple first-order coupling produces proton NMR signals of the kind that you have been shown. There are situations where peak splitting does not produce these types of clean signals. For this course, you do not have to worry about these more complex types of signals. Now, a demonstration on how to calculate simple J values. Here in the upper left, we have the molecular structure for diethyl ether. These proton NMR signals you see correspond to the protons in diethyl ether. In the interest of getting more practice, you may wish to spend some time figuring out which signal correspond to what protons in this structure after the end of this webcast. If I want to calculate the J values for these signals, I have to be able to convert these ppm values to Hertz values. How do we do that? The first thing we have to know is what is the strength of our spectrometer. In this example, these signals were taken in a spectrometer with a strength of 500 megahertz. Now, remember that ppm is calculated by taking the chemical shift of a peak in Hertz and dividing it by the strength of the spectrometer, which is measured in megahertz, in order to give us ppm as our chemical shift. If I want to take the chemical shift of a peak in ppm and convert it back into Hertz, all I need to do is take my chemical shift in ppm and multiply it by the frequency of the spectrometer instrument. Knowing this information, let's calculate the J value for this triplet on the left. It is important to note that the J value for a signal is independent of which two peaks you decide to use to calculate it. For example, in this triplet, I could take this distance between peaks from the leftmost peaks to the middle peak, or I could take the distance from the middle peak to the right peak. Either distance will give me the same J value. Let's say I decide to use this distance on the right. What I could do is take this value, plug it into this equation, and calculate the shift in Hertz. Take the second value, do the same thing, and then subtract the two values. That is a perfectly valid way to calculate the J value. What I prefer to do is, instead of converting each of these signals into Hertz individually, is to subtract them and then convert them into Hertz. Let me show you that process now. That is the chemical shift of my middle peak in ppm. Now I shall subtract the chemical shift of the right peak in ppm. And that gives me the difference in chemical shift in ppm. Now if I wish to convert this into Hertz, I simply multiply this by the strength of the spectrometer, which gives me a value of 5.8 Hertz. When talking about J values, we always round to the tenths place. This means that the J value, the coupling constant for this triplet, is 5.8 Hertz. Let's do the same thing for this quartet on the right. I shall again pick the two rightmost peaks. Remember, it doesn't matter which two peaks I select. Either distance between adjacent peaks should give us the same J value. Do the same calculation. That's my difference in chemical shift in ppm. Now let's convert it to Hertz by multiplying by the strength of the spectrometer to give me a coupling constant of 5.8 Hertz, again rounded to the tenths place. Notice how these values are identical. This is because coupling constants are reciprocal. If these two signals result from protons splitting each other, they must have the same coupling constant. In this case, that should make sense, because these protons on the methylene and these protons on the methyl must be splitting each other. They must possess the same J value. Now, let's say you selected a different distance. For example, if we look at this triplet on the left, what if instead we selected the leftmost peak and the middle peak? What J value will we calculate there? What I had told you is that we should obtain the same J value. But if you use these numbers on the screen, you would instead see a J value equal to 6.0 Hertz. Why is that? These chemical shift values are given to us by a computer. How accurately the computer is able to measure the middle of each of these peaks determines how accurate our calculated J values are. So what happens if the J value you calculate is different than the J value I calculate because I selected a different distance? Your answer will still be acceptable. So long as your answer is within the threshold, say plus or minus 0.2 Hertz, your answer is fine. Those values are about the same, and any difference is a result of the numbers given to you by the computer. Now for some practice. Go ahead and calculate the coupling constant for this signal here. Remember that these values in blue up top are measured in ppm. Pause the video and calculate the J value, the coupling constant, for this sextet. Welcome back. Let's see how you did. For this signal, I am selecting the middle two peaks. This is not a requirement. You can select any two peaks that are adjacent to each other. I just happen to be selecting the middle two. Do some calculations. I get the difference in ppm, and then I multiply by the strength of the spectrometer, which this time is 600 megahertz. Make sure you pay attention to the values the problem gives you to get a value of 7.9 hertz. Now your value might be slightly different. Your value might be a little bit more, it might be a little bit less. But so long as you selected two peaks that were adjacent to each other and used the values given to you by the problem, your answer is acceptable. What makes this useful as a tool to us? Remember, J values are reciprocal. That means that if you have two signals that have the same J value, you know that the protons belonging to those signals must be adjacent to each other. You learn about connectivity this way. Before finishing this webcast, we have to talk about something that was glossed over in the previous one. In the previous webcast, we discussed why two protons that are next door to each other split each other. When trying to predict how many peaks HA should possess, we learned about the n+1 rule, where if we have a hydrogen that has n number of neighboring equivalent hydrogens, the number of peaks is n+1. There is a word in this that I didn't discuss last webcast. That word is equivalent. In most cases for aliphatic protons, the equivalent portion of this definition is not relevant. Unfortunately, not all protons are simple aliphatic protons. Consider a situation where we have two protons, HB and HC, splitting proton A. Now consider what would happen if HB and HC are different types of protons. What should we see for the signal for HA? If HB and HC did not interfere with HA, we would expect to see a singlet, one signal. Of course, we know that's not true. We know that HB and HC will affect HA somehow. On the previous slide, we were reminded of how, when HB interacts with HA, we should see a doublet. Now, what happens when we include HC in this scenario? We know that, like HB, HC can either be aligned with the magnetic field of HA or opposed to the magnetic field of HA. Therefore, we should see splitting similar to what HB performed. But we already have two peaks, so what should that splitting look like? You would see something that looks like this, where each of these peaks resulting from HA splitting with HB are now split by HC, producing a pair of doublets, or what we call a doublet of doublets. An example that would cause this type of situation can be seen here in the middle. If we look at this green proton, we can call that HA. If this green proton is HA, it is being split by this blue proton and this purple proton, which are not the same. Therefore, this green proton would show up as a doublet of doublets. If you look at 1-propanol, our example from the Proton NMR webcast part 1, we saw that we had different sets of equivalent hydrogens. Yet, for these red protons here, we didn't see a complicated splitting pattern that resulted from multiple J values. Why is that? This is because for most aliphatic protons, even if they are not equivalent, such as the purple and the blue protons, the coupling constants are close enough that we don't see this type of splitting. Therefore, the N+1 rule still works for simple aliphatic protons. How can you, the student, figure out whether to use the N+1 rule or to be on the lookout for multiple J values? I will inform you if multiple J values are present. For this course, you simply need to be aware that non-equivalent protons can give different coupling constants, resulting in more complex splitting patterns. Our last topic for this webcast will be on how we can use these J values, these coupling constants, to tell us something about the structure of the molecule. We already know that if signals have identical J values, they have to be splitting each other. We can also use the numerical value of these coupling constants to tell us the orientation of some protons. If you look here in this blue box, we have two protons in various orientations. These orientations are shown via Newman projections. In a Newman projection, we are looking straight down a bond. This intersection here represents the front carbon we are looking down, and this circle represents the back carbon of the bond we are looking down. The angle between these various bonds is called the dihedral angle. If you look at these two protons, our dihedral angle is 180 degrees. If you look at the middle structure, where we have simply rotated this proton to a new position, our new dihedral angle is 60 degrees. If I rotate this proton again, it is now at 0 degrees. The dihedral angle between protons is important because the dihedral angle determines the strength of the coupling. If you look at the table below, we see a number of protons in different orientations and the resultant coupling constants between those two protons. The greatest value of these coupling constants is if we know something about the structure of the molecule already. If we look at the bottom of this table, we have proton A and proton B on the same carbon of an alkene, on different carbons of the alkene, but on opposite sides of the double bond, what we call trans, or on different carbons in the alkene, but on the same side of the double bond, what we call cis. You can see how each orientation has a different coupling constant value range. If we know we have two protons that are part of the same alkene, we can know whether they are on the same carbon, they are trans, or they are cis, simply by looking at which range their coupling constant falls into. Do not memorize these values. If they are needed, they will be provided to you, but do know how to use them. To recap this webcast, The coupling constant, or the J value, of a signal is a measurement of the strength of the interaction between two nuclei. This value is calculated using the distance between peaks in a proton NMR signal and the strength of the instrument used to generate those signals. J values are reciprocal. Two protons splitting each other must have the same J value. It is possible for signals to have more than one J value. This occurs when a proton is being split by two significantly different types of protons. And finally, the dihedral angle between protons on adjacent carbons determines the strength of a coupling value. And you can use those values to try and identify the relative positions and orientations of the two protons.